So how do you know if we have audio or not? Okay, you're going to check it. All right, so we are getting ready to start, and we're going to do an audio test to our stream and see if that's working or not. No, we want to see if the audio is working to the live stream or not. So I'm talking so that we can have audio to the live stream. I'm not saying anything important except making noise. He's testing the YouTube channel to see if we have any audio or not. Okay, I'm still talking. Okay, got audio to the stream. Okay, very good. All right, good enough. So, okay, so do we have a volunteer to go tell the people in the planetarium we're going to start in 2 minutes? Kayla, you going to do it? All right, thank you. Yes, the planetarium is open now before the meeting starts. If you want to go see it, no. Okay, if you want to go see the planetarium, it's open now till the meeting starts. It may be open during the break, I'm not sure. But, and then they're going to take it down after the second part of our meeting. So that's my understanding, but it's definitely open right now. And we're going to start here in about a minute. Should have seen us last month. I know. I give them their heads up. All right, thank you. Millions and millions. What? I did not notice that.
Johnson Space Astronomical Society general meeting.
Wow. Yeah, maybe we'll get a bunch of strangers come in here.
Hey.
I was so jealous.
I had the Northern Light.
I recognize that we're missing some people. How many people were actually in there? Without the rest of our crew. Okay, it's after 7:30, so we're gonna get started. Welcome to the October meeting of the Johnson Space Center Astronomical Society. I'm like the Rodney Dangerfield of the astronomy world. Okay, so before we get started, since we're back at the Lunar Planetary Institute, if anyone has never been to one of our meetings before and is willing to admit it, Put your hand up. Susie, right? Okay, so how did you hear about our club and what's your interest in astronomy?
At work, we get a newsletter.
Came to the right place. So which group are you in at JSC?
I support Colin.
Oh,
Hamilton Sunstream.
oh, yeah, the suits, right?
Yeah.
Excellent. Wonderful. Okay, I saw Aaron.
I just had someone,
Now you have two?
well, it's not mine.
I think it was mine. Hey, you got to hold on to those tickets because we got some really good door prizes. You guys gonna want them. Okay, I saw at least one more hand right here. Oh, two more. Which? You in the orange shirt.
Yeah, so I'm Mark Gillespie.
Oh,
I work here at the LPI.
excellent. And you are a speaker in February, right?
Yes.
So there he is, guys. You can take a look at him and decide if you want to come in February or not. Thank you. Nice to see you. And yes,
My name's Josh.
professional, you actually found a way to make money in astronomy? Good enough. Excellent. Anybody else? Good. Welcome. Oh, okay, hold on. Let's see here. All right, so this is our agenda for this evening. I'm going to kill the lights. While we're meeting here in person, we're also live streaming our meeting. And so if you are on our live stream, you can submit questions to our presenters today by either sending an email to jscslive@gmail.com, or you can enter them in as a YouTube comment in the YouTube section if you have a YouTube comment section, if you have an account that will let you do that. And our producer up here, Trevor Quinn, will get those questions and he'll provide them to our speakers. All right, very important. The green button blues. Used to be the red button blues, but now it's the green button blues. They changed the color of the button out there. When you leave the building, there's a green button on the side. The doors are locked, okay? So get the doors to unlock, you have to press the green button beside the doors, and then the doors will unlock and you can open the doors and go out. But the doors are locked. If you try to force through them, don't do that. And the doors cannot be open for more than 20 seconds. Otherwise, the alarm goes off and drives all the rest of us crazy here. And it goes for a long time, which is very bad. So doors can't be open more than 20 seconds. Use the green button to unlock the doors to be able to get out. Also, please do not go beyond the rotunda area or the great room area out here. Our agreement with the Lunar Planetary Institute is that we won't go wandering around the building. There's a silent alarm supposedly down the hall that can get set off, and it's our agreement is we stay within this area, the rotunda area, and not go beyond that. So please abide by our agreement. Okay, so first up tonight, we have Kayla with What's Up in the Sky.
Ah, there we go.
The mouse is a little.
All right, so today I got a couple of objects that we'll be able to read. stars. Well, they can come visit. Now I can't see what we're doing. All right, so what we're going to do to try and find it, of course, the moon will be the easiest way to find it. Also, if you look for the constellation of Cancer, this green circle that you see here, that is actually what you would see if you're using a pair of binoculars, roughly about 10 by 50s. If you want to see the M44 itself, now M44 is actually going to be about twice the diameter of the moon. But the moon might actually kind of cover it out a little bit because the moon's going to be much brighter. So go ahead and bring your binoculars or your telescope just below the moon itself, and then towards the bottom of your field of view, you will see M44. Like not moving around. Cool. All right, anyways, to find this, again, like I said, we're going to be looking for the constellation of Cancer. It's going to be right on the top of its shell. This is an example of someone that was using almost a 6-inch, it was 155 refractor, and this was the field of view. This is what they were able to see with the stars. So this gives you an idea of what you'll see, because again, of course, we're not using the Webb telescope ourselves. M44 was found first by Galileo, or was looked at telescopically first by Galileo in 1609, and then Charles Messier added it to his list in 1769 when he measured it in the night sky. The next one I have for you is also on the 18th. This will be in the late evening, and that's Juno is going to start coming to a full stop. Juno is one of the larger asteroids in the main belt. Juno has currently been in a retrograde motion in the night sky and is about to come to its peak and then appear to go western again. This is a magnitude 8.6, so it's not going to be the brightest thing to see. It's also going to be on the smaller size. So this will be a little bit harder for you, and you'll definitely have to do some star hopping to find it. Juno is roughly 230 by 288 kilometers, and it goes from, and its orbit is around 208 or 2 AUs at its close approach, and 3.5 at its farthest approach from the sun, and it's about 4.3-year orbit. So to find this, we are going to look towards Aquarius, the constellation of Aquarius, and we're actually going to be looking kind of, if you have the image, it's always going to be where his thigh is. So we're going to be looking towards these stars. This is also going to be Lambda, Tau, and Sigma. Those are going to be the stars that will make a triangle, and you will see it go on its approach to its easternmost and then start going back the other direction again. These are medium bright stars, so not every map you have will actually have them pointed out. So you might have to go through a couple of different maps to find ones, because as you can see in this map that gets published through Sky and Tel, it actually is only showing one of those 3 stars. Anyways, asteroid Juno was discovered in 1804 by German astronomer Carl Harding. And what you're going to see is really just a small, faint, what will look like a star. But it will actually move, where if you're tracking maybe one of the other stars, you'll see it start to move across your field of view where the stars are staying put. It won't be very fast. It'll be a little subtle, but that's how you'll be able to see it. We also have the Orionids coming up. This is going to be, a week from today, right? The 21st. This will be pre-dawn as well. It's actually going to go from the 26th. It's already ongoing, and it will go to November 22nd. we're not expecting this peak to be super bright, super big. But if you get into some darker skies, you will see 10 to 20 bright, fast moving stars or meteorites. And that's per hour. And what I always liked about the Orionids, this is the one coming from Comet Halley. So this is when we're passing through its debris. So how do we find it? The easiest way is to find Orion. Orion is one of the more recognizable constellations that we have. So we'll go ahead and look for his elbow, because he's usually holding up his club above his head. So look for the elbow, and you should see that being the point of origin for most of the meteorites. So just put a little elbow into it. Again, Orion's really easy to find. You can always find the bright Betelgeuse, or you can find the 3 stars in his belt. And then it would I accidentally covered it. It would be right about here. All right, we also have Mercury returning to the eastern horizon. This will be before sunrise, so all you early risers will have a lot of things to look at this week or this month. We are going to have a very old crescent moon. It's only going to be around 1% illuminated, so it's just going to be a little thumbnail. And it's going to be about a thumb's width above the planet Mercury. The duo will be seen in the pre-dawn twilight. With binoculars will be easy to see it. Just don't look at the sun, please. So this is showing you the same thing. It's going to be low on the horizon. Make sure you don't have trees or buildings next to you. Mercury, the moon, just a little sliver. This is your binoculars, 10 by 50, kind of a standard size for astronomy. And that will be how you find that. And again, just because I like to do this, expectation versus reality, you're only going to see just a small little speck. You're not going to see the nice, beautiful messenger photos. All right, any questions? They're only estimating 10 to 20 bright, fast-moving meteors an hour. Yeah, I mean, it's not going to be one of those lenses where you're getting like 100 an hour or anything. It's not going to be a nice storm. It's looking like this one will be a little bit less active this year.
Okay, my apologies. I forgot to mention, guys, when you're up here trying to find a laser pointer, there's this online thing you do with the mouse there, and then the people looking on the YouTube channel can see the laser. My apologies. Oh, don't you stand up here yet? I'm good. Okay, so our main speaker tonight is Leonard. He's chomping at the bit. I haven't even introduced him. He's already down there. But before he starts his talk, I want to tell you a little bit about Leonard Ferguson. Positive things, uplifting things. Yeah, we won't tell the other stuff. All right, so Leonard Ferguson, this guy right here, is an active amateur astronomer with a particular interest in our sun and variable stars. He is a longtime volunteer at the Houston Museum of Natural Sciences George Observatory, conducting classroom presentations during public star parties and assisting with the operation of the domed telescopes. I read that wrong, sorry. Anyway, okay, he's active in Fort Bend Astronomy Club, assisting with educational programs and helping to support and organize club meetings and activities. So join me in welcoming Leonard Ferguson.
Right. First thing, how many active solar observers are familiar with? So there's going to be some numbers. Yeah, so if you're I'm going to cover some of that, but I guess to start with, we kind of, this is a talk that a version of it I originally put together about 10 or 15 years ago that I was actually giving out at the George. And then I guess back last winter, Doug was posting photos of his progress doing his radio telescope. And so kind of started up some email conversations, and I kind of mentioned doing the sudden ionospheric disturbances. So kind of got the talk out of the backup disk and updated it. And so we'll see I've kind of added a little bit more space weather and a little bit less of the sudden ionospheric disturbances. So anyway, we'll cover that in a little bit. So right now we will move on to the sun, which is going to be the center point of all of these that we're going to talk about. So I think you all know the basics, the distance and the diameter. Composition right now, it's on the main sequence fusing hydrogen into helium. So it's about 92% hydrogen. The remaining is helium and a few trace elements. So, volume and mass right there. Core temperature is believed to be about 27 million degrees. So what the sun is doing right now is fusing about 600 million tons of hydrogen every second and fusing that into 694 million tons of helium. And the remaining 4 tons is converted directly into energy in light and heat energy. So to put that in perspective, on Earth, that is the equivalent energy of about 2.5 billion nuclear power plants running for an entire year is what the sun's putting out every second. So lots of energy. So just a shot here. This is what we've known as the sun for most of human history. And then starting about a few hundred years, maybe up to 1,000 years, we started to have sunspot observations. Some of these go back to about the year 1150 or so, were some of the first sketches of sunspot observations. So, and then, of course, since we've now got modern instruments up there, we've got a lot more information. So, but going back to about the 1500s or so, they first started to identify the primary solar cycle, which is about 11 years, and indicated by the number of sunspots. So the sunspot count's the primary indicator. Now, there are other cycles that are superimposed on the 11-year cycle, and there's a lot of debate on some of those, but the 11-year cycle is the primary cycle. So we've hit solar minimum a few years ago, and we're now headed on the increase of solar activity. If you keep up with it, we've been having some more activity recently, and we're getting close to the midpoint of what is called solar cycle 25. So I'm going to cover this slide. So if you see the blue graphs there, those each represent a solar cycle. And right here on the end is where we're headed on the increase there for solar cycle 25. So we'll come back to the modern minimum, but there were observations going on back here in the 1700s. And some of the names, Cassini, after he moved to the observatory at Paris, had a team of solar observers. They were doing sunspot counts, and of course Galileo before that, back in the early 1600s. So here is what a little bit of what we can observe today. We have visible light here where we just see those sunspots, but if we look at a different wavelength, then we can see the magnetic activity. We can see what's going on behind those sunspots in wavelengths that, again, up until we've got modern instruments up there, we couldn't see. And then here's X-rays. So there's a lot of more intense energy going on behind those sunspots than what the earlier astronomers saw right here. Back to the Maunder minimum here. Is everybody familiar with the Maunder minimum and the little ice age? So this is back to that one graph there. There were very few sunspots for mainly this period of 1645 to 1710. So to give you a perspective, from the last part of the 1600s, say from 1670 to 1699 or 1700s, there was a total sunspot counts for that entire period of about 50. And a normal solar cycle, that would be about 50,000. So very, very small percentage. There was barely enough sunspots for them to identify when the solar maximum was. So now the Little Ice Age also coincided with this. And the Little Ice Age actually started earlier, probably back into the 1400s and extended into the 1800s. So, but it was very pronounced. Environmental effects, cold winters, crop failures. There's records of the glaciers advancing and snow peaks on the mountains that were much lower than normal. So some of the agriculture in Europe, they had to either change crops or actually had to move south so that if they wanted to keep maintaining the same crops, because the crops would just not survive. So back to this graph. So right in here is where the that all this period here, but this right in here is where that very low period was at the end of the Maunder minimum. And then the reason we've got some red plots in blue. So we had a scientist named Gustav Sporer in the 1800s. He actually went and had a team, and they actually formally identified the sunspot cycle. And they went back and they decided that 1755, February 1st, would be the start of solar cycle 1. So we get the solar cycle 1 starts there in 1755. And then again, this ends here at solar cycle 25, where we're at now. So the cold winter showed up in the artwork of the time. This is by Hendrik Averkamp, called A Scene on the Ice. This was painted in 1625. Way back here, we hadn't even hit that deep minimum yet. And so it was already working its way into the artwork of the time. But this, say again? No, this is in the Netherlands. So that was one. Now this is the River Thames. So this is called the Great Frost of 1883-84. So this is an engraving, but this is a river. So people would they would actually, you can see the drawing there. They would actually set up. It was actually a fair out there. They would have shops and cookouts and everything on here. So this is how they dealt with it. The ice, the reports of the ice here in 1683, the Thames was frozen over for about 3 months from November to February. And the reports are that the ice was at least a foot thick. There are some reports that it may have been as much as 18 inches thick. So it took here's another one here, same time period, called the Thames Frost Fair. So now what they've done in modern times is they've gone back and looked at tree rings, looking at carbon dating, and using beryllium-10. So the idea with beryllium-10 is that it is kind of counter to solar magnetic activity. But beryllium-10 is created by solar rays hitting the Earth, and the magnetic activity it protects us from the solar rays. So as beryllium-10 goes up, they're calculating that as a minimum or less solar activity. So using all these and using tree rings and ice cores and all, they've gone back. Now this chart is reversed from the other one. This is from now going back through back in time. So you see the Maunder minimum, and there's the Sporer minimum, which is about the 1400s or so. So you see that wasn't as deep as the Maunder minimum, but it was a little bit longer. And then the Wolf minimum, and going on back. So they went back, I think, 10 or 12,000 years and identified a number of these. So the current thinking is the sun may be spending about 25% of its time in one of these extended minimums. So that's less solar activity. So now we can move to intense solar activity, solar flares, and coronal mass ejections, or CMEs. So these are the most powerful events in our solar system. And so we often hear, if you keep up with it, we hear about the CMEs because they're particle based, and those particles travel about 1 million miles an hour. So they take about 4 days to get here. So there's plenty of time for that to get into the news feed. But the rays, which are X-ray and UV based, they travel at light speed. So we don't hear about those as often. So here on the left here is a animation of what we think goes on under the surface as sunspots form up. These are magnetic fields that start forming in the plasma underneath the surface of the sun. And as they start to, the complex starts to grow and these fields start to combine, and that plasma starts to gather up along here, similar to these coronal loops here. And at some point, if the mechanics are right, that whole complex will collapse. And like you saw in the animation, it strands material off the surface of the sun. That's what gets blasted off of the surface into space. So down here is a extreme ultraviolet animation from SOHO, and you can see the CMEs there. There's a couple of them going to the right and the left. The rest of this is just regular solar wind, just constantly streaming off into space. That's all particles that are moving past us in space. So, yes, sir. I think I think it just happens to be where this animation was taken, but well, I think it's just the angle it's observing from. So if it, yeah, it could be any of those. So yeah, you can. Because the
materials.
and the sunspots tend to move closer to the equator as you approach solar maximum, and then as you start going back towards minimum, they go back towards the poles. So the more intense or the more active areas during solar max should be near the equator. So that kind of goes with what we're looking at here. Okay. Okay, so here's just a diagram of our magnetosphere out in space. We've got the Earth over here to the left, and all of these magnetic fields that are concentrated at our poles, and this all protects us from most of this radiation that's coming from the sun. And then you get the solar wind streaming there from the left. The way I kind of like to, you've seen a rock or a tree in a running stream, and the water's flowing past it and going around it, and you have kind of an active area here, and then you have kind of a calm area in the back or behind the flow of whatever it is. So here's an animation. I believe this is from the TRACE spacecraft with different densities of the solar wind coming by, and you can see the Earth there, and you can get an idea of how our magnetic field actually changes as these different densities move past us. This is only about a 4-hour animation here. So, and you can see the difference. That's a pretty good distance. The Earth is 8,000 miles across, so it's that area behind us is a pretty good distance. So there's a lot of influence even out into space. Okay, so all of this together is what we call space weather. And so space weather was the term really came out about the 1950s, but it's been about 20 years. It kind of started turning into kind of its own science. So now we've got a lot of resources online where there's a lot of predictions and a lot of information on what the sun's doing at any given time. And I've got the last slide here. I've got some links on that. But mostly, so there's two different ways. So space weather, sometimes they'll refer to it as the overall influence of the sun throughout the solar system, but the original definition was kind of confined to the Earth environment, exactly how we're affected directly on Earth by the sun. So here's some of the things that can happen. We have the atmosphere can actually, this energy actually heats the atmosphere up and makes it expand. So sometimes it expands enough where it can actually put physical drag on satellites and cause the orbit to decay. Geomagnetic storms, that's the aurora. These Empower systems. So has anybody heard of the Carrington event? So that was probably the largest one of these events known was 1859. That was, there's reports of telegraph operators being shocked from energy being induced on the wires from this energy. Some of the telegraph stations actually caught fire from the buildup of energy. So when this material hits us, all of our power lines, it looks from space to this material looks like basically a long wire. So you've got, just like an electrical circuit here on Earth, you've got a moving field crossing a wire, and it induces energy into that. Our modern systems have protections against that, but still, if it's a powerful enough event, there could be some effects there. So, and the same thing with satellites. You know, everything is GPS these days. Our phones and our cars and everything are routed through GPS, and this can not only cause problems with the satellites, but it can induce errors into the signal. And same spacecraft malfunctions. Astronauts up in the space station, occasionally they have a special area in one of the units that has more shielding. So if there's a large event, that will actually send them into that area for protection. And then ionospheric disturbances, which we'll cover in a little bit more detail. So these are, we have different regions of our ionosphere. So what we can do is, or what we're going to cover here is specifically related to the D region, which is the lowest region. It's from about 30 miles up to about 60 miles. And it's a region that exists only when the sun hits it. So when the energy from the sun, the particles ionize and create that layer. When the sun goes down, the particles are very, they recombine easily, so that layer disappears. So you have the D region lower, then you have the E region, and you have the F region, which is way up there. So, but what they found out back in probably about the 1950s is that the D region is very good at propagating low frequency radio signals. So there's the lowest point, and then the F region. So during the day, there will actually be two F regions form up also because of the energy from the sun. So here's the D region right here, which will reflect or absorb certain frequencies of radio energy, and then different waves here will reflect off the E region. So I don't know if anybody's ever turned on like an AM radio in the middle of the night and picked up some station way off that you'd never pick up during the day. Well, the D region absorbs those frequencies. So that's why we only hear local stations on AM during the day, because the D region absorbs those. When the D region disappears, if the propagation's just right, then they'll reflect off the E region and we can hear stations from a long way away. So ham radio operators, this is all useful to them for communicating around the world. So I just kind of put up a couple of sketches here from, if anybody's an AAVSO member from the solar division. They had some sketches here of how to build this. So there's several different receivers or tuners that you build. And I'm going to cover this kind of quickly, but you basically can take a loop antenna and tune this to specific frequencies. So the good ones, the powerful ones, are to use the VLF transmitters that the Navy uses to communicate with the submarines. So those are very powerful, and they propagate easily. So now we're not listening to the transmission, right? We're just listening or just measuring the intensity of the signal as it reaches the station here. So by doing that, we can tune a loop antenna and just build a simple receiver to pick up that frequency, run it through an A to D converter, and then just measure a voltage current with a computer, or sometimes they would use a strip chart recorder. And you get a trace. This is very old, so this is also from the AV. So this is a very simple, you can build this on a little 2x2 inch PC board here. And this antenna here is about, say, 50 turns. I've got a picture here in a minute, but just build a simple loop antenna and using a couple of simple circuits. I did build a few of these. I never had much luck with them. So, but I know there were other people that did. So, but the trace up there is kind of what you get here. This is, I've got some better ones, but this is a sunrise pattern, and this is a sunset pattern, and this is probably a little solar flare right here. So the one I had success with, and so there's the loop antenna, is one. So back in around 2007, Stanford Solar Center actually engineered a number of these for the International Heliophysical Year 2007, and the idea was to get these out into colleges and high schools and get solar science out in front of students and out in front of the public. So I did bring one along here just to give you all an idea of how big it actually is. It's actually pretty small. This one's assigned to the George Observatory. So we actually got one of these and we ran it as a public exhibit for several years out at the George Observatory. So, but if you get this thing working, this is what your trace looks like. So here is, mouse does not work. Anyway, over there on the left, all that's all just nighttime noise. So that's when the D region is not there and the receiver's just picking up random noise, and the same over here on the far right. So that double hump right there, about a quarter of the way over, that's called that set pattern. And that's formed as the Earth is turning into the sun and the sun's hitting that upper region, you get that first increase. And then as the sun clears the horizon, you get a decrease. And then this is the actual sunrise right here. And then you get an increasing signal over the day as the sun passes overhead and keeps the ionosphere energized. And then there, about 4/5 of the way over, is your sunset pattern. So here's kind of an overlay of that. And then if you happen to catch a solar flare, there's 4 of them. Those are probably C class, maybe some M class, medium class solar flares right there. So the vertical, so what happens is when a flare hits the ionosphere, it immediately changes the properties, and we call this sudden enhancement of signal or sudden ionospheric disturbance, same thing. So it immediately changes the absorption, and so you get an increase in radio signal.
Is that just, magnitude when you go?
Yeah, those are just voltage level, the voltage that's measured. So, and actually, the actual signal is very small. It's probably 0.2 of a volt to about 0.5 volt, and then most of your receivers actually amplify it. So, but you get that as the absorption of the ionosphere is altered, you get that immediate enhancement. So it always makes a sawtooth pattern. And then as the particles recombine up there and it returns to normal, then you get slow decay and back into the curve of where your normal trace would be. Yeah, it's some of them may take maybe if it's a big event, may take several hours to return to. So this whole, depending on where you're at, that whole tan area there in the middle, could be about 12 hours. Right. Well, the immediate effect is suddenly, and then it decays. So with these, so Stanford kind of turned these over to Society of Amateur Radio Astronomers. They don't actually offer this one anymore, but they have one called a Super SID, and they offer it in a kit. But Stanford still maintains a database of these. If you use their software, it'll actually upload once a day or however you into. So then you can actually upload your data into the database, or AAVSO solar section will also take your data. They have a different. You have to go in and actually plot these and figure the onset of the event and the time of the peak and estimated intensity and all that. And they have a different report form, but they will also take your data. So, but I did go into the Stanford database and just pulled. These are all from yesterday. So that one in the middle, you can see that's a pretty good trace. The one up at the top, not sure what's the other, maybe that one's antenna issues or something. And then the bottom one. So these are not all perfect traces like I was showing here. That middle one's a good one. But here's another one. So that top one, you see that dropout. So these VLS stations also generally have a maintenance day once a week. So that is that dropout on the top. So they'll take them offline for the entire day. Sometimes you'll get that sunset pattern, and then you can see that. And then a pretty decent trace on the in the middle, and then another one. That one looks like maybe they didn't have the gain turned up enough. Yeah, it kind of sounds like a modem, the old modem when you connect to your phone, it'd make all that squealing noise. And this thing actually has a phone jack where you can, yeah, but it's just random noise. Yeah. So now we've been having solar flares recently. So I pulled a couple. So this top one, that looks like a small flare, that's probably an M class there. And you can see down here at the bottom, different station, they caught it as well. This one, I'm not sure if that is the same event or not. Sometimes what can happen is the polarity, the event can be reversed. It depends on how close the receiving station is to the transmitter and the angle of whether it comes in. Sometimes a sky wave will override, and some of it comes in on the ground wave. So sometimes you do get reverse signals like that. So have to interpret this quite a bit sometimes. So we got that. So just kind of going back to space weather here, we're increasingly dependent on satellites and GPS technology. And all of these, even our power systems are all they're all electronic. So this all kind of acts like static electricity to all these electronics. Of course, now we're getting ready to send astronauts back to the moon. And then once they leave our magnetic envelope, they're going to be out in open space. So they're having to take a lot of attention to this and designing these new spacecraft. So in addition to the information we already have, I think we're going to see more and more alerts and all due to space weather in the future. I think that is all I have. Horses, if you want to take a look. So that's all I've got. That came off of, I think that came from Stanford. Most of these came from Stanford. Sorry. All right. Thank you.
Okay, Leonard, thank you for being our speaker tonight. No one's seen Ron, right? Nobody's seen. Those come tonight, but. All right, so maybe we'll see Ron next. Ron actually has our DVD library with he loans out DVDs about various astronomy related topics. Really cool. And okay, so the meeting after the meeting. After we get done here, we're going to get together at Mod Pizza and continue discussions of astronomy and other topics. If you don't know where Mod Pizza is, you come out here, go down Bay Area Boulevard, shoot up Middlebrook North, turn left on Clear Lake City Boulevard, you go past El Dorado, and right in front of the HEB, there's a Mod Pizza. And we'll get together there. And I went by today, like they asked us to, and I told them we're coming tonight. So last time we showed up and there was like not very many people working there. And so they said, hey, next time, let us know you're coming. So I went by and told them today that we're going to come. So we're going to take a short break and then we will continue on with the second half of our meeting. I think we'll take doing pretty good, probably 10-minute break. And I think the planetarium may still be up. I think she said she was going to do it. Oh, they took it down? Okay, thanks for telling me. No planetarium. 10-minute break. We'll get back together in 10 minutes. Okay, our 10 minutes are up. We're gonna get started again. Yes, we are. Time to start. All righty, boys and girls, take your seats. All right, we'll get started. Hey, we're trying to get started. I know, everybody wants to talk to you. You're so popular. We're getting started. Lights are going down. You must take your seats to be safe. Oh, that worked. I'll have to remember that one. Hey, everybody back? Close enough. All righty, so welcome back to the second half of our meeting tonight. So I have a couple members' minutes here. In fact, guys, listen, in the future, if you have something you'd like to present that lasts about a minute, pretty quick, we'd love to have everybody participate. So if you have something you'd like to come down here and tell us about, let us know, and you can do a member's minute at one of our future meetings. Okay, one fish, two fish, red shift, blue shift. This is my member's minute for this evening. Where's Wes? Where is he? There's Wes. Wes, this is for you. Okay, so at our last, Wes is a professor over at UH Clear Lake, right? Adjunct, good enough. All right, so I was standing up here minding my own business at the last meeting and telling everybody about my radio telescope that Leonard alluded to a minute ago. And we were talking about things we could do in our area. So I'm showing my radio telescope I've made in the backyard and showing my MATLAB plot over here with my results. And showing my data, and I was claiming some of the stuff is red shifted and some of it's blue shifted because you can see these things going back and forth, right? See, like some of those, they're moving around. They're not at one frequency, they're moving back and forth. And somebody in the audience says, how do you know that you're not just measuring the rotation of the Earth with your radio telescope in your backyard? And I looked at Brandon and I said, Brandon, help me, help. And Brandon he explained all this, but then I thought, you know what, I should understand that and I should be able to explain this to when people ask me something like that. So I members met to address why do we know that we're not looking at the rotation of the Earth and we're claiming it's actually redshift and blue shift. Okay, so there's the Earth. And if I take the circumference of the Earth, which is 40,070 kilometers, and I divide it by 24 hours. Now, you guys know that as fixed point in space, our rotation once around the Earth is not really 24 hours. It's actually a sidereal day, which is how long? That is so close. It's 4.09 seconds, Justin. What is wrong with you? Yes. 23 hours. I looked it up for you. 23 hours, 56 minutes. Yeah.
Well, I know that from memory.
Yeah, and 4.09 seconds is how long a sidereal day is, which is how long it is when the Earth turns around based on a fixed point space. So it's not exactly 24 hours, but we don't care because we're going to do this rough calculation. So if we're standing here on the equator, we're zooming around at 1,670 kilometers per second. Okay? What? Per hour. Oh, thank you. Thank you. Thank you. Kilometers per hour, not per second. That would be bad news. Oh, okay. What? Okay. I gotta tell you guys something. Okay. Anybody here watch America's Funniest Home Videos other than me? Anybody ever? Okay. Did anybody see it last Sunday? Nobody. I'm the only one who got to watch this. Okay. So I was watching America's Funniest Home Videos last Sunday, and the guy that's the host said that that's the reason that we stay on the Earth is because the Earth spins. Okay. That's what he told the whole world. So, all right. It's not my fault. All right. So anyway, this is supposed to be a minute. Let's see. So what causes redshift and blue shift? It's caused by the Doppler effect. So if I have sound waves, I have, say, for example, I have a fire truck or something else, and the speed of sound is constant in air. But as the fire truck moves towards me, the sound waves bunch up, and the wavelengths get shorter, the frequency gets higher, the pitch sounds higher. When it moves away from me, the speed of sound is still constant, so the waves are spread out, the wavelength is longer, and the frequency is lower. Same thing when I have a celestial object when it's coming towards me or away from me. But in this case, rather than the pitch getting higher and lower, we see a blue shift as the frequency gets closer, gets higher and gets closer, goes to the blue side. And as it's moving away from it's red shifted as the wavelength is stretched out. So that's why we have red shift and blue shift. And there's a nice little formula you can use, which this formula is not exact, but it's an approximation. So the change in wavelength, which is, okay, let me start with this. There's a laboratory wavelength, which is what this thing would be if there was no motion between these two objects. They were fixed, distance between them. That's our laboratory wavelength of something radiating some radiation. Then the change in wavelength is how much it changes from that laboratory wavelength up or down. What we're trying to get is the radial velocity, which is how fast something moves away from us or how fast it's coming towards us. And the speed of light is constant. Okay, so that's my formula to be able to measure redshift and blue shift. So here's one of my plots from my radio telescope from my backyard. And so I'm going to claim that this thing is getting somewhere up around 1420.9 megahertz. So neutral hydrogen, what we call 21 centimeter wavelength, it's actually this frequency. And when you calculate the wavelength, the actual wavelength of neutral hydrogen is this, okay? But my measured frequency was this 1420.9 megahertz. Calculate the wavelength, and that wavelength is this, all right? So I put those in my little equation, get the delta wavelength is this, my laboratory wavelength is this, and by knowing the speed of light, I can calculate and find out how fast this thing was moving towards me in my backyard. I get 375,328 kilometers per hour. Yes. All right. And I'm going to say that 328 kilometers per hour is much greater than this, which is how much it would be from the Earth turning. So that's why we believe that our radio telescope is actually measuring blue shift and red shift. That's do you believe it, Wes?
I think it's gonna take a while.
Okay, wait a
I
minute.
mean, they're obviously one is larger than the other.
What? Yeah.
I said, I'm picturing which is which.
This is my measured one. This is the rotation of the Earth one.
Yeah, roughly by a factor of 200.
Yeah.
So
So
you're getting a blue shift from your source.
I'm getting my blue shift from right here. Here's my plot of my frequencies directly from the radio telescope. And if I take this thing down here, and I'm going to claim that's about 1420.9 is the top of that. So that's the frequency that I'm measuring, the radio telescope.
Are you measuring the red?
I'm just saying this plot right here. Don't let the red make you think it's red shift or blue shift. This is blue shifted, but it's red. That's just the color of the plot. Don't let that bother you. Don't let that, oh, guys. No, wait, time out. Look, as the frequency gets higher, it's blue shifted, right? Just because it's red, it doesn't mean it's red shifted. It's red, it's blue. Okay. What?
You need a very high velocity.
Right.
The Earth's rotations.
Right. That's what it is. The rotation of the Earth is small compared to this velocity of this thing. But okay, so what I'm saying here is 1420.9. That's my frequency. Convert that to wavelength. I get this wavelength. This is the laboratory wavelength, right? So this guy here, this wavelength is longer than that wavelength. Everybody agree with that? No. Wait a minute. The other way around. The other way around. Right.
For those who weren't here for the previous
Oh. I don't want to do that. You want me to tell them how the radio telescope works?
Yeah.
It's a higher frequency. It's
That wavelength there is longer.
this, no, this is short. That's a
Oh, no,
one.
I'm sorry,
This
that's
is a
one.
two. Yeah. This is a one. That's a smaller number. One is a smaller number than a two. Yeah, right. So Al, listen, what are you asking me? Because I don't want to blow you off, but
Are you just measuring?
okay.
Hydrogen is at 1420.
1420.4058 megahertz is neutral hydrogen. Yeah, so it's like over here, 1420 point somewhere in like there. See, that's neutral hydrogen. But the way this is like a spectrum analyzer. You take the radio telescope you set up, and this thing just sits here and scans through these frequencies like this, you know, and then it tells you the amplitude of each one. Is that what you're asking me?
That's what I was asking.
Yeah, it's like a spectrum analyzer. It's just sitting there and going, and it goes blips up and it goes down like this, like that. But the reality is this thing integrates like this integrates like over 900,000 samples for each one of these. Because if you're doing this with a Wi-Fi dish in your backyard with a Raspberry Pi running this whole thing, you know, there's got to be something that makes this work. And what the key is, just like when we do in astrophotography, when we put a whole bunch of pictures together to cut the noise down. This is like 900 and some thousand samples, you know, added together, you know, for every one of these points here on this graph. Is that what you're asking me?
Yes, thank you.
Okay, all right. Okay, Wes,
Before the big hill?
this one?
No, the little tiny one, right before.
Yes,
It seems to be right at the frequency.
it is.
Oh,
Yeah, see, it's not all, because, you know, when you're looking, okay, guys, when we're looking through the Milky Way galaxy, we're in it.
yeah.
So we're seeing the stuff that we're inside, which is neutral, because it's right, it's near us. And then I'm looking all the way through the whole galaxy, and I'm looking to the other side of it. So it's like there's a big variety. Yeah, you're getting a whole gob of the stuff that's near us and the stuff that's far away, all of it. Yeah. So I'm saying, but the farthest one out here, John, I'm saying this is the fastest one because this is the highest frequency that I got on this particular moment. So Wes, are you convinced, or do I have to? Yeah. Well, what? Okay, this is actually taken on the same day. The summer Milky Way is the Milky Way that's up. You know, when Sagittarius is up. That's the summer Milky Way. The winter Milky Way is the one around Orion. So on the same night, you see both the summer and the winter Milky Way on the same night. It's not really summer and winter. It's a summer one because the one you see in the summer, and the winter one's one you see in the winter. But if you stay up all night long, you see both of them. It's true. You guys know that you can see. You guys know you can see Sagittarius and Orion the same night, right? Yeah, you know that. You can do that. Wes, can I move on? Are you okay with this, or you got some? Okay. I did this for you, so I want to make sure that you're happy with this. All right, that's the end of that one. That wasn't a minute, I'm sorry. It's what? Oh, a question.
Not a question, not real, but you have.
How did you know that? Were you here last time? Okay, yes. Okay, I do. On my, yeah, it is so much fun. And yes, and if you can't find me, my webpage is on here on the end, but I'd be happy to talk to you about it. On my webpage, I tell about how I made this thing. Okay, but it's just, I mean, okay, this whole radio telescope costs less than about $150. Okay, and I run on a Raspberry Pi, and I go inside my house and let this thing run. I let it run for like a week and a half. Okay, and I remote control it through a Raspberry Pi. It is so much fun, and it actually works, which is incredible. So, but yeah, this is what I was telling you guys last time, is this is actually the point here where you can show where it shifts from red shift to blue shift. So I'm claiming that this actually is a way to measure how far we are out from the center of the galaxy. You can actually measure this in your backyard. You can actually go out there and do this and prove to yourself how far we are out from the center of the galaxy with this thing. About 1/2 to 2/3 of the way out. Okay, so Ovidio, look at this. How far do you think that point is? No, I mean like and a half. Like this is 0 and this is 1. How far do you think that is? Because see, that's where it shifts from red shift to blue shift. See?
60%.
So that's what I'm guessing, something like that. And that's what my understanding is. We're like 1/2 to 2/3 of the way out from the center of the galaxy. That's my understanding. So I'm just saying that to answer the student's question, trying to get him inspired about radio astronomy, you can actually make one of these things yourself, which is incredible to me to think you can actually do this in your backyard and get this to work. So you guys should do this like as a lab or as like a capstone project or something like that at your school. This is fun and educational too.
I know it's not the first
Really?
time.
Yeah, really, you guys really should do this because it's doable and it's really, you learn a lot from doing it. And you learn about, electronics, you learn about radio transmission. It's really it's a good project. Okay. Any more questions about that? No? Okay, next members minute, Vandenberg 142. So there's a guy, Sidney Vandenberg, who lived in Canada, and in the 1960s, I think in 1966, he published a catalog, 158 reflection nebulae. And so, there's all these nice catalogs of celestial object, the NGC catalog, the IC catalog, the Messier catalog, all kinds of Caldwell catalog. People are trying to make lists of celestial objects, but this is a catalog of reflection nebula. So, what?
Used to come across the border.
Is that right? This guy? Oh my goodness. Oh my. Did you ever meet him?
Yeah.
Oh, wow. Well, that's really cool. You do a presentation. You sound like you have more interesting things to say than we do. Okay, so this is actually IC 1396 Cepheus. So some time ago, Kayla actually did a presentation about what's up in the sky, and she was telling everybody about Herschel's Garnet Star, right? Herschel's Garnet Star, right? So this is actually Herschel's Garnet Star here that Kayla was telling you about, one of her things. And then right next to this is this gigantic nebula, IC 1396. So a couple things about this. One thing is this is 6 degrees across. And so this has got, I'm going to guess that's about maybe 2 degrees across, right? Okay, so how big is the full moon? Half a degree. Yeah, so think about it. This is like 4 full moons wide. This thing is huge, right? Gigantic nebula in the sky here. 4 full moons across. So IC 1396, I actually took this picture with a camera lens and a modified DSLR. And if you zoom in on this, there's actually this region right here. And you look right here, there's this object that's called the elephant's trunk. So you guys can look at that and decide if you believe that that looks like an elephant's trunk. But that's a zoomed in version of this IC 1396. And this is taken with a camera lens. But recently we had some really nice weather here, and we had low humidity and clear skies for about a week and a half. So I was able to take a picture of the same area. This is the elephant's trunk, but taken with a 1600 millimeter telescope. And this is a narrowband image of the same region. So you go back here, see? There it is. That's a RGB image with a DSLR, elephant's trunk. And that's it in narrowband with a longer focal length telescope. Okay. All right, one more thing related to this. Also, while we're talking about trunks, there's actually this area here called, some people call it the trunk-like pillar. This is NGC 6823, which is open cluster, and next to it or around it is this NGC 6820, also known as Sharpless 286, emission nebula, trunk-like appearance. This is also a narrowband image. In both these images, these were about a week and a half worth of integration time. You can only get about 3 hours of them at night, and then they're done in narrowband. So it's about 20 some hours each one. I would share that with you. All right, that's it. Any questions about that? Okay. All right, thank you. Next up, we have David with Star Party News.
We're not doing this remote. All right, October Star Party News. October 1st, we had a gathering outreach event at Magnolia Creek Golf Club. And on October 8th, we had a little drop down event that cropped up at Challenger Park, and I've got slides for those coming up. Tuesday the 18th, we've got a Star Party at Alvin Community College. That is, I believe, a Tuesday night. Trevor tells me it's going to start at roughly around 7, and it will go until the event kind of peters out. Moon will not be in play, so you're just going to have to be able to hunt whatever DSOs we can find. These are on the calendar on the website. 27th through 30 October, we're at Fort McCavitt. That is a confirmed date. Yes, it is also overlapping, unfortunately, with the El Dorado Star Party. Usually we like to daisy chain these so that one is on one weekend and the other one is on the other weekend. Originally, Fort McCavitt was supposed to be the weekend before. Ken and I kind of got our lines crossed. They said, I'm sorry, Fort McCavitt is 27 through 30. So unfortunately, these two are piled on top of each other. Also, the 29th, Leonard and I are actually trying to run a limited A-Day at the George Observatory and would appreciate help. We definitely need help with deck scopes. And it's going to be limited because we're only going to keep it as a cap of about 500 people. So the days of 2,000 people coming through the door are gone for a number of reasons. And that I don't want to take too much of the evening talking about that. We could talk about that at MOD. November 4th, we have an event at the Hack Winery. November 16th is an event here right around the corner, center fields throw, roughly through those trees. We've got a Star Party outreach event at UHCL. December 3rd, we're back at Magnolia Creek. They've wanted us to come back, and I'll be emailing that as the event gets closer. The moon will actually be in play for this event, even though we can probably see some other things, possibly Orion by December. I have to double check, but the moon will definitely be in play. Discussions are underway also with Manville Junior High School. They would like an event sometime in November. Mazatlan 2024 are going to be April 5th through the 9th as an Eclipse land tour. Tamara Letty, Ted Blank, and myself are going to be leading 3 land tours of 40 people each. It is currently sold out, but if you're interested, you can get on the wait list. Information for that to be on eclipsetours.com. Magnolia Creek turned out to be real fun. We had about 75 patrons, clear night, with good views to the south and east. They had a first quarter moon up. I definitely really want to thank Mark the cellist, Doug Holland, Jim Wessel, who came out. I haven't seen him for a while. Reed, William Conley, Bob and Leslie Eaton, and long had not seen John Gorduck in ages, and happy that he showed up too. So I've got Mark, and there's Doug over here, Jim Wessel with his back to us. This is a nifty little place, and it's got a very good, as I said, got a very good view to the east and south. A lot of people, kids were there. Jim was having fun with his light bridge. Reed's drinking on something. There's Leslie showing probably the moon through her binoculars at that time of night. A lot of us have started off on the moon and then drifted elsewhere. Doug was just getting set up here. Mark had a number of people around his scope, and this one's got Bob getting set up as well. It's a nice little area. Started about 6:30. We go till the crowd pretty much thins out. And it was usually by about 9 o'clock. And as I said, we've got another date with them on December 3rd. Challenger Park Camping Outreach cropped up within a week. They actually did email, I think Doug and myself earlier, and I have to be honest, it kind of fell off the radar a little bit, but it actually came together within a week. Bob and Leslie Eden kind of helped spearhead it. Chris Randall was there, Reed Clouser, Bob Hammond, who I haven't seen in quite a while, and Paul Hanegraaff for the old timers of the club, if that name rings a bell. He came out of the woodwork to show up for this one, and William Conley. Bill brought this, said he acquired this Edmund Scientific little reflector all of the day before. Paul Hanegraaff, Leslie, Chris Randall. There's no pictures of Chris Randall or his big scope because he was the one taking the pictures, and Bob Eaton. And it turned out to be a very good event. Now, for some that don't know, the club used to do about 2 or 3 outreach events at Challenger Park. But actually that kind of came to an end when I was president back in 2010. It just kind of fell off. The chemistry wasn't there anymore. But now a new precinct commissioner, according to Leslie, wants us there to possibly come back 2 to 3 times a year. So this may be finding its way back onto the calendar. And it'd be a good event because it would be an event for recruiting members, because it's literally the other side of Bay Area Boulevard and the other side of the freeway.
How's the light?
They're going to work on taking some lights off, but we got to work with that given where it is. It's somewhat not quite as, no, the golf course is a little bit better in that regard. But yeah, we will have to work with the lights. And honestly, that is why inside daylight savings time, I always try to put the moon in place so we can get around the light pollution and gives us a target to show the public. All right.
I got a question on the.
Yep.
Party. Do we have times yet? Do we know enough?
Most of them will probably be around 6:30 and move and go on past that point. Actually, I'm going to take that back. I think it's closer to 7 because they have to get the being able to park and not get parking tickets worked out. We'll know more about that as that comes down. And then the one for Alvin, Trevor and I will get that information out. Hopefully tomorrow. Get those details out. Reed, and then Bob Hammond again with that wonderful AZ Pro mount. And told you we shouldn't have left the car here 50 years ago. Look at all the tickets. That's all, folks.
All right, thank you, David, for being our Star Party chairman. That's a lot of stuff to do. Okay, so this is actually Kayla's idea. I think it's a good idea. We did this sometimes, and sometimes I think we forgot to do it, but we're gonna have a thing called Star Time, which is called Show, Tell, Ask, Respond. And basically, if anybody has something they'd like to tell us about, or you have a question you'd like to put out to the group, now is the time to do that. Oh, did you, B? No. Do what?
Turn on the light.
Another light.
Oh, turn on lights. Okay.
No.
Ah. Okay, all right, let's have it.
You see that asteroid.
Change the orbit by about 30.
Anybody else got something you want to tell us about? You need, sorry, one more time?
Who's all gonna be at the Georgia Observatory?
David, you want to take that?
You're talking as far as astronomy there?
Right here.
Was there an email that came out for this meeting?
Did our emails?
No, Rob.
Okay, there's two email lists. There's one set up just for the meetings and one for others, the meetings and other things. Normally you get everything? No, I sent out an email on Wednesday about this meeting. So do you get the normal JSC Google Groups emails?
Yeah, I just did.
And also, that reminds me, there's a sign up list out here as a clipboard. If anyone wants to get our emails, put your email address on there. We'll be sure to get you on. But if you're not getting emails, let us know, because there are some people that don't get them. Gotten dropped from the group? Oh, I thought we dropped some people from the list. Okay, listen, have you put your name on this list lately? You got it on her now? Okay, we'll make sure that we get you on the distribution, because there are some people that got dropped from the list, so maybe you may have been one of them. Okay, anybody else have something they need? Show, tell, ask, respond? Yes.
So, the,
And what time is it again? 7:30. 7:30. Very good. That's a good time. Oh, even better. Thank you. I'll show, tell, ask, respond. Topics. Okay, sure. All right, well, because I have one. All right. Show and tell, right? Okay, so this is a calendar that I made with a bunch of my astronomy pictures in it. Now, the reason I'm telling you guys this, because there's some other astrophotographers in our group, and I think it's a really good deal. This is $20.33 total, shipping, tax, the whole bit. You use this code 20cal. This is with Bay Photo. You can look them up, Bay Photo. But it's pretty nice. I mean, it's 11 by 17, and the picture quality is actually pretty good compared to other prints I've had. I'm just letting you guys know about this. I'm going to give these away as Christmas presents, not to you guys, of course, but to other people. I give these away as Christmas presents, and it actually turned out pretty good. So if any other astrophotographers in our group are interested in cool Christmas presents for your families and friends, Bay Photo, $20.33. I think it's a pretty good deal. Alrighty, next month, we're going to have Paul Maley, and this is actually going to be a remote speaker. So this is going to be a wild one. Paul's going to be remoted in here. He's going to do retirement astronomy from Arizona. We're going to somehow put him on the screen and hear him and have other speakers at the same time. And Trevor's going to make the whole thing go and make it work. And it's going to be a huge success. So we're just going to see how that goes. All right. Now, after we're going to do door prizes, and we're all going to go to Mod Pizza directly after this. But first we're going to do some door prizes. All right. So take out your door prize ticket. And the first one is 617. Probably that lady that left like 2 seconds after the meeting. John, come on down here. Okay. So do you take
put on the bumper?
Oh, on your
card?
windows.
Yeah. See, this one says, I'm an astronomer. What's your superpower?
okay. What else do you want?
Hold on. This one is Astro Imager. You probably don't want that one.
Wow.
But I have one more you might like. Have scope will travel.
I kind of do that. Yeah.
So you can have one of those, or
Or-
do you take Sky and Telescope magazine?
No.
I had the October issue for Sky and Telescope magazine because they
Okay.
sent me two.
Oh, so you have to, I'll take up to date.
You don't want to hear all the rest of the choices?
No, that's it. I'll just go with.
Okay.
Let
good
somebody
enough.
else take it.
All right, good enough. All right, next one is 620. Are you guys listening? Get over here. 620. Okay, wait a minute. Let me show you. I have data in astronomy.
Okay.
Now, wait a minute. Telescope and Techniques. This is actually a pretty good book.
I think I'm gonna get that one.
Or you can have a decal for your car.
Oh, no,
I'd
I
go
think-
with this one.
I
It's,
think I like
it's a
that.
good book, actually. I have that one. All right, good enough. Thank you. Okay, you're welcome. Okay, now you guys are looking at your numbers, right? Yeah, okay. Okay. 601. Oh, are you kidding me? Okay, hold on. Okay.
Have telescope will travel, please. Thank you.
Oh, yeah, we have, do you want to have telescope will travel?
Yeah,
Oh, man, okay. You know, I've been trying to get these decals away for so long.
I got a nice big window in the back of my Subaru too.
Okay, there is Has Telescope will travel?
Yeah.
Okay,
It's
good.
perfect.
Actually, I won these at the Texas Star Party myself, but I don't want to put them on my car, but that's yours.
Thank you.
Here, hey, Aaron, here's the envelope. Put it in.
Sweet.
All right, very good.
Appreciate it.
Excellent. No, I trust you. Okay, so I'm gonna give away one more door prize. One more door prize. We had good door prizes, right? 615. Oh, I gotta give away some of Kayla's. She's got the best door prizes. 615. I didn't even open Kayla's box yet. 5. 15? Anybody? Oh, is it you? Is it you? All right. Come on down here. Our solar system, okay? You keep that one. Hang on. to it. Bought these, so these are really nice. She's got, this is a mouse pad that shows like the, it looks like, what is that? Artemis 1, thank you. I got Artemis 1 mouse pad, or she also brought these nice things, Kepler spacecraft, the metal thing, like a model you make, or the Hubble Space Telescope one. Would you rather have a model, or would you rather have hear that? Mission Control exclusive. Woohoo! All right. So that's it. So see you guys. That's the end of our meeting. See you at Mod Pizza here as fast as we can get there. Thanks for coming.